Hi class, what I want to do in this lecture is just walk you through a triple integral using spherical coordinates. Just like with the double integrals and triple integrals, what I found is that, or maybe you're noticing this too, is that the hardest part of the problems tend to be setting up the bounds of integration. And then once you can figure out what the bounds of integration are, the actual integration methods aren't that difficult. Okay, so here's the problem. Let's evaluate the triple integral over e of the function dz, okay, where this e is defined as the upper half of the sphere given by x squared plus y squared plus z squared is equal to 1. Okay, so the upper half of the sphere is where z is positive. Okay, that's great. Looking at this equation here, what we're seeing is that the center of the sphere is the origin, and the radius of this sphere is 1. All right, so what you have to figure out is the bounds of integration here. Okay, so let's start with rho. What is rho defined as? Well, rho is the distance from the origin to the top half of the sphere. Well, that's easy. That's just the radius. So we're going to go from 0 to 1. Piece of cake here. All right, what is theta then for setting this up? So theta is the rotation in the xy plane. Well, if you think about a sphere, it's if you just look directly down and project the sphere onto the xy plane, it's a full rotation. So it's going to go from 0 to 2 pi. If you would look down in the xy plane, you would see a circle. So that's how it's going to go from the 0 to 2 pi. All right, the phi here, that's actually the hardest part for this problem. So a common mistake here would be to go, all right, phi has to go from 0 to pi, but that's not the case. You actually only have to go from 0 to 90 degrees, and the reason you can stop there is because you're then rotating that around fully. So you're catching that second half there, so you don't need to go from pi over 2 to pi. So you only need to go from up to 90 degrees here. All right, so then this just ends up getting set up as the following, okay? D phi is the last integral, so that's going to go from 0 to pi over 2. D theta is going to go from 0 to 2 pi. And D rho is going to go from 0 to 1. All right, we know that our formula tells us to put rho squared sine of phi. This part here, 8, is from here. And z, using our methods to change from rectangular to spherical, z gets replaced by rho cosine of phi. All right, now you got this set up. Now it's a pretty straightforward integral. I like to take sine of phi, cosine of phi, and write it as 1/2 sine of 2 phi, kind of using the double angle formula instead of eventually going to use a u substitution to solve. I just think it's a little bit easier. So when you do that, the 8 times 1/2 becomes 4. Rho squared and rho gets you rho cubed. Now this is a piece of cake to integrate. All right, so you're going to do d rho first. So you're going to keep the 4 and the sine of 2 phi constant. So that just ends up integrating as rho to the 4th, and the 4 cancel out. When you go to plug in 0, that's gone. So the 1 just makes it 1. So you're really just left with sine of 2 phi. Now here, when you plug in d theta, you hold this constant, so you just get theta sine of 2 phi evaluated from 0 to 2 pi, which is just 2 pi sine of 2 phi. Incredibly easy to integrate here. This just integrates as you're going to need to use just a u sub here to integrate the inside of sine if you want. Or this just integrates to minus pi cosine of 2 phi evaluated from pi over 2 to 0. Well, plugging in pi over 2 and 0 here and watching out for the negatives, you end up getting pi plus pi, which ends up just being 2 pi. So again here, the actual integration part, piece of cake, the setting up the bounds of integration were the difficult part here. But I hope seeing this one example helps you as you go to try these problems on your own.